All right, folks, just percolating some thoughts on the chain rule. So I want to add a little bit of context to what was the name of the video I did? Chain rule through the lens of integration. I think that it's one of the hardest things to see is why it works and how it works. So here's just the beginning of a thought process here. So, creating, don't worry about the letter C here at the moment. So creating functions can obviously come from accumulating area under a curve. So why don't we look at how the accumulation of area under a curve happens in each instance, and see if that might be a better way of teaching the chain rule, and I haven't crunched the numbers in a way that probably can show you each and every step, and hopefully I'll have some time to do that. But let's just take, and I don't know if picking a trig function was the best choice at this stage, but sine cubed x squared plus 2x plus 7. And what do we teach in calculus for the derivative of this? We teach what? 3 sine squared x squared plus 2x plus 7. And then we multiply by the cosine of x squared plus 2x plus 7. And then we multiply by 2x plus 2. Right? I mean, that's the general process that I think most people use. And I'm not sure at this stage that it's the most effective. Because if you pick a number and you just wanted to evaluate the function, well, you'd drop in a 3, and you'd have the sine of 22, and then you'd cube it. I mean, that's the order that we evaluate in. So if we're going to find rates, why don't we follow the same order and create new axes, and expand our concept of really composites. Okay, so if I pick 3 and I'm looking at a sine curve, right? Well, 3 is roughly here, right? It's just a little, probably 0.14-ish above 3.14. So it's almost a 1-to-1 rate of change there. So, we use 3, but we're not at the sine of 3 anymore. We're at the sine of 22, which is over here. And, I did 3.14 times 7, 21.98. So we're really near 7 pi. And, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7. So I counted it properly. A little shout out to Lawrence Welk. And so what's happening there is we have an associated rate of change in this function. How's it changing there? And that's really determined by this function as well. So we really have a new axis here of 2x plus 2. I mean, that's really what's, I picked a bad spot here because I can't draw a rectangle here. But let's just draw one here. Let's just say that, it's not dx anymore. It's, if you crunch the numbers, it's 2x plus 2 dx. That's how the width changing. And the associated height, this doesn't have any height here. You can't see it. It's just a very small negative value. All right, I'm probably losing folks at this point. But it seems to me that we should really stick with inside out. So the first rate of change is 2x plus 2, right? And then the rate of change of the sine function is the cosine function, which is x squared plus 2x plus 7. So we would need to get the cosine function drawn and find out where we are on that curve and how the area under the cosine curve is accumulating. And we can crunch those numbers. That's, I guess, what I'm getting at is we can actually crunch some numbers and see what's going on. But I think you have to do it through the lens of integration. Now, if you go to that video, I actually crunch some numbers. I think base 10, or I say base, I've been teaching a lot of exponentials and logs right now. So I've been using x equals 10 because it's a nice friendly number. And crunching those numbers is a little easier because I'm not a calculator guy. I really dislike the calculator. I really do. And stronger mathematicians need it, I know, when you get to upper levels. But I'm not teaching upper levels. Okay, so I like to really try to see what's going on the old-fashioned way, the marker. But where was I? Oh yeah, so I got to finish this off, right? So we still have the cubing function. So we got to look at 3 sine, and I'm writing this in parentheses like so, I think. So I don't need that one. So where was I? 3 sine x squared plus 2x plus 7. Because I think when you're just learning this, it's better to talk about the function, maybe even put this here. That is the derivative of cubing, right? 3x squared. It's all about surface area of cubes. All right, so I'm babbling, but I wanted to just get the discussion started about different axes, and I'm hoping I can draw some really good pictures and crunch some numbers slowly, maybe using 3.01, and I'll have to use a calculator when I do that. Although there's some nice patterns, right? So if you did 3.01, and you wanted to know how the cubic was changing, how many O's did I say? Let's just do 5. 4 O's and a 1, 4 zeros and a 1. So 27.00012.00009.0000001 somewhere in there. Anyway, there's some geometric principles behind all this stuff. And I'm, as I said, babbling. So I'm going to get this stopped immediately.